Okay, do you hear me now? Yes, I'm speaking. Do you hear me? I'm speaking. This is a test. Okay. Do you hear me? Do you hear me? Okay, great, perfect. Thank you, Chandra.
Can you hear me now?
Yes. Thanks everyone for
Yes, I'm speaking.
comments. Perfect. So, all right, let me continue. Maybe perhaps I should start from the beginning for those who didn't hear me, aka most of the people. So basically, it was an intense course. The main idea was to give you all the necessary ideas, the background knowledge that people in the high energy astrophysics and basically in the astrophysics academia are currently using. And it was an interesting but complex subject to dig in. So it required some preparation to make. I mean, the introductory sessions. So we had one lecture, one introduction lecture. It was about basically the physical concepts that basically people in the astronomy field are currently using, the basic physical principles that high energy astronomy is based on. So such as the concepts of electromagnetic theory, the polarization, and the modern physics. We dived into those topics. Well, I'm not planning to go into them one by one right now, but if you're interested, I can forward you the course. But basically, if you want to be involved in astrophysics, if you want to be involved in the astrophysical academia, you need to get used to the physical concepts. What I mean by that is you need to make your hands dirty with mathematics and playing with those things. The lectures that will be provided you as an introduction part are just meant to give you the basic idea, and then you will need to forward yourself. You will need to further educate yourself in this field by reading textbooks. Maybe contacting me. I can also navigate you in some different fields. So basically, the first week, we gather around all the physical concepts that we will be using later. So because there are two ways of doing that. Like I could either provide you, just give you all the information one by one, or I could start the thing that I was planning to tell you, and then when I talk about something you don't know, I could actually open that idea while I was going into there as well. But I think doing that would actually change our course, like change the course of our system. So in order to avoid that, we introduced these physical concepts prior to the thing. If you have questions about these introductory sessions, feel free to ask me right now, and by the end of my speech, I will happily answer them. So when this physical introduction ended, we went to the second part of the course, which was basically talking about the astronomical concepts. We actually, by the knowledge we had with the pre-introduction, we dived into the general general astronomical sources that are currently being researched in the high energy astrophysics field. So basically, I'm talking about this high energy a lot. Let me just make a little definition here, although these definitions are actually also available in the course. So basically, we have light is consisting of some electromagnetic wave. So these electromagnetic waves that are consisting our whole spectrum have different various types of energies, various ranges of energies. So when we have a light beam coming to us from space or anywhere else that has high energies, we call them basically high energy physics. So when we are dealing with X-rays, gamma rays, these kind of highly energetic radiation, we are talking about high energy physics. So when we have a source, an astronomical source, an object, beaming us, sending us a light with very high energies in forms of gamma rays, X-rays, charged particles, cosmic rays, these kind of sources are generally cover the field of high energy astronomy. And there are specific sources, actually many different sources send us these energies. Well, for example, there are also planets, we even get X-ray data from some of our planets as well. But we mainly get this X-ray data in specific types of objects. For example, the disks of black holes, or neutron stars, or surfaces of neutron stars. Getting that knowledge getting that data from these sources revolutionized the way how we understand these sources. This is why predominantly we think these kind of sources, which we call them X-ray binaries, because they predominantly send their light in the form of X-rays. So they hold the main part of high energy astronomy predominantly. It doesn't mean that for example, neutron stars don't send light in any other forms of energy. In fact, they are discovered in radio waves. Justin Burnell discovered them. But the conclusive information we get from those sources are usually from X-rays. We also have sources like supernova explosions or their remnants. We also get gamma rays and X-rays from these kind of sources as well. So I'm not planning to go into full detail of them, because covering all these things actually lasted about 2-3 hours. So I'm planning to keep this meeting short and navigate you through the course, basically. But the overall idea of the second lecture was basically making an introduction about the sources, the astronomical objects that we are currently investigating as X-ray astronomers, X-ray astrophysicists. This was the main idea. So if you have any questions in the second part of the lecture, also feel free to write it down and I will happily answer them. And then once we finished this second part of the lecture, we jumped into the third part, which was actually a kind of a little break from all those beam of very intense information. So while talking about these kind of things, while making an introduction or giving you a background knowledge in any kind of field in physics, there are two ways of doing that. You can either start with the chronological part and then start giving the information as humanity learn those information. This is one way of doing that. The other way is to just don't considering anything about when this thing was discovered and giving this information from basic to complex. So you don't worry about the time or the chronology, but you worry about how simple is that in terms of the concept. So in this course, I mainly tried the second one. I didn't want to go to the timeline of the events, but also thought that it would be nice to have a little historical background to this field. So the third lecture was actually aiming for that. Basically, it was meant to give you a historical background about high energy astronomy. Basically, high energy astronomy is mostly the astronomy in 20th century, especially observational astronomy in 20th century. So we gave you a little recap about the astronomical issues and the problems that astronomers are facing in the 70s, 60s, 80s, even in the 20th century. And then it should make you realize that how young this field is. We basically managed to get vast amounts of information by the end of 20th century from black holes and neutron stars. We are actually in the very beginning of this field, so there is a lot of opportunity. The aim of that lecture was to give you that main idea, basically. While providing those ideas, I also wanted to provide you some engineering information and some technical details about the telescopes, because basically the CCD-like detectors, the systems, optical systems, well, I don't think they call them optical systems because they are not optical, they are not visible to human eye, but basically the detector systems of these kind of high energy telescopes, X-ray telescopes, gamma ray telescopes, they are pretty advanced. The technology that is behind that idea of detecting X-ray and gamma ray sources are very important for electronical engineering, for signal processing. So I also wanted to emphasize on that fact as well. Especially in the 1990s, in the early times of 21st century, we developed more and more sensitive and precise technologies for us to catch X-ray photons. Most of them are actually based on very basic idea of photoelectric effect, which is also fascinating because just by one single concept, you are able to get a lot of information. Just you have layers of silicon material, and when an X-ray or a photon goes into that layers of silicon atoms, it actually excites some of the electrons on that layer. So when that electron is excited, it passes through the semiconductor and generates a photoelectric current. And this current, by measuring the voltage of that current or the effect of the electron flow, you are able to get the energy of that single of that single photon. And then by looking at the time of that photon arrives, and then looking at the energy and therefore frequency of that incoming photon, you are able to get a lot of information. Because even if you have like 1,000 photons coming from one source, which is really, really low, compared to, like, for example, right now, I think millions of photons should be coming to you from this computer, because billions maybe, because the light is over there, the sun is over there, it's coming to my screen, and then it's actually coming to some places and then reflecting back to me and then reflecting there to you directly. So we have vast amounts of photons coming to you right now, to your eyes, but generally in these kind of high energy sources, we only have like 1,000 photons sometimes, or 2,000 photons. These advanced technologies that we developed in the past, by in the past I mean in our generation, we managed to create conclusive evidences about many different things, many different concepts and phenomena that were discovered these times. Although it is not high energy, it is radio, but with this general knowledge, the ability to increase the amount of knowledge you can gain from one single photon, this actually enlarged our capabilities, and this concept allowed us to see the image of the black hole, for example. And although it is not technically a part of high energy physics, it is a part of the multi-messenger astronomy. I wanted to also talk about, I talked about in this course, the cosmic rays and also gravitational waves as well. Well, basically, I think for multiple times throughout this course, I talked about one important issue. What we used to have in the classical astronomy, we used to have one person climbing to an observatory, doing this very romantic solo observations, and then going to the spectrograph and then plotting it, like very, very manual processes, very analogous manual processes. Well, sometimes there are still many telescopes, many observatories in the world that function with that way, but it was very usual for an astronomer to work on one single part of wavelength or one single part of the sky. This was what we used to have. But right now, thanks to new developments in radio, in microwave, in infrared, in ultraviolet, in X-rays and gamma rays, we are able to learn about the universe from vast different types of knowledges. This opened up a new field. This opened the field of multi-wavelength astronomy. Now astronomers are usually working in groups of different researchers. They are looking at one single source from different wavelengths and acquiring knowledge. This is what we call as multi-wavelength astronomy. It was a primary way of learning and information in the 20th century. And now we are able to catch the particles that are emerged from an event in the sky. And by catching those particles, we are able to get an additional information. What we used to say to all the people was that the primary source of knowledge of astronomy is light. So if there is no light, you are not able to see me. If there is light, you are able to see me. We were talking about that. But if you somehow magically get a particle from when I'm speaking, you're able to get more information. So right now, light isn't the only source of knowledge for an astronomical source in our universe. This is remarkable. We are able to catch particles which are in the forms of cosmic rays, in neutrinos and positrons and electrons and protons and alpha particles, gamma particles. So by catching those highly energetic massive particles, well, not massive, but particles that have mass, so basically we are catching those in our particle detectors, in our astroparticle detectors, and we are acquiring knowledge. As I am talking about this, actually, in the core of stars, there is a process called Cno Cycle, which I think I'm briefly mentioning it in the course. Basically, the process of star producing the light producing new forms of atoms. Basically, after hydrogen and helium burn, star goes into a cycle of creating carbon, nitrogen, and oxygen continuously. So we should be able to get tremendous amounts of neutrinos from that process. And we managed to actually, I think last month, while I was giving this course, we discovered the very first neutrino arrived from from a Cno cycle of our sun. So we proved, not only we proved that the Cno cycle is actually happening in our sun, we also scientifically proved the existence of Cno cycle thanks to this astroparticle development. So technically, this is conventionally this is also a part of high energy astronomy as well, but it is not this information is not acquired through the messenger of light. We did not receive this through the electromagnetic waves. We received this through a solid particle. Even though it is neutrino, it is very interesting particle. It is not like a conventional proton or neutron, but it is still a particle. So we have another messenger right now in astronomy that allows us to get information. The other part of this messenger was the basically the proof of Albert Einstein's general relativity. One of the proofs of Einstein's general relativity. Basically, the concept that mass actually bends the space-time continuum, and because of this bend, many different effects are changing. Different masses due to gravity, how gravity bends the space-time, different masses are interacting with each other, and also light and time is also interacting with this. So when we have this understanding, this new understanding of our universe, we learn that when two massive objects, actually every object, but basically for us to be detectable, two massive objects, when they revolve around each other and then merge, this emerging energies, rotational energies, come out to us in a form of wave, which we call it as gravitational waves. So this provided us another messenger in astronomy. We used to have only light. Now we have light, cosmic rays, and gravitational waves. So this enlarged our view of how we see astronomy and how we see the universe, and basically allowed us to go into we were just walking around the shores of the cosmic ocean, and now we are building a boat. We can maybe sometime in the future, we are able to, by enlarging, getting new instruments, better and better precise instruments, we can maybe finish our boat. And then, by mean of boat, I don't mean to say a big motor yacht. I'm just saying we can slowly go to the depths of the cosmic ocean, but it's taking time. So basically, in the 21st century, we are basically looking at the vast horizon, and the horizon seems endless. The possibilities of new discoveries seem endless. So it is a perfect time to get into the astronomy, basically. So in the third course, by going back to our initial topic, this was our initial plan to give you this motivational idea. So basically, how these modest steps allowed the most interesting part of astronomy to develop. Basically, people who were using hydrogen balloons to catch astroparticles, and then this evolved into neutrino observatories, Cno or other observatories. And then in the fourth part of our course, I wanted to show you a little bit of how data analysis is being conducted. Since this was not meant to be a workshop on X-ray analysis, I just demonstrated you a very basic. I think I provided you a black hole with a disk. So by looking at this X-ray source, you were able to do some data reduction. I provided you some online sources, online databases. So basically, we have a nice thing that NASA actually makes most of its observations public, except if it's a proposal. Then in this case, they are sending this data to the astronomer, and then that astronomer makes some publication. They are waiting for a while, and then when they get the credit for that discovery, they are making it public. But even with a policy like this, after tens of years, we have enormous amounts of data from different types of stars, especially in old telescopes like Chandra. So if you look at Chandra X-ray Observatory, which was actually named by the famous Indian astronomer Chandrasekhar. So with the help of Chandra Observatory's database, we are able to get a vast amounts of information for free. You can just download it, given that you know how to do data reduction, cleaning, and analyze. But apart from that, you are able to get these information. So I basically showed you some online resources to where to get these information. I think instead of going through the Chandra data analysis, I also showed you some information about nicer data analysis as well. Because yes, the main idea is that Chandra telescopes, all telescopes like Chandra, have large amounts of databases. But at the same time, there are more modern observatories. There are more modern ways of doing X-ray analysis, and nicer telescope is one of them. Nicer is a small, nice instrument that is incredibly sensitive. The instruments that they are having right now is really capable of doing amazing things, especially getting information from the surface parts of black holes and the X-ray binaries. So thanks to that, I think we analyzed some X-ray sources with nicer telescope. I showed you basically all those telescope information, all those databases are combined. So it is possible to just go to the NASA website, High Energy Astronomy HESARC software. You can go and dive into the database. If you know what source you want to look for, you can check the public archival data that is available for you to analyze. So we picked one X-ray source, and then we made some data reduction. We calibrated that object, and then we introduced redistribution matrices, response matrices, and then by combining those things, we acquired a spectrum. We extracted the spectrum from the event file. Basically, in astronomical observations, we call our observation documents as event files. It is basically a pile of document that keeps the information of at what time, which photons arrived, and how much energy do they store. So basically, it is a collection of those things. So we extracted the necessary information we need to achieve, the intensity of light, and then the wavelength of light, or the frequency of light. So we basically were able to get at which energies, how much photons or how much intensity of photons arrived. So we acquired the spectrum. And by looking at the spectrum, we looked at the chi-squared analysis of some of the conventional models. I think in the introduction part, I introduced you with the idea of power law and other famous ways of explaining X-ray spectrum or X-ray sources. So power law is one of the strongest of them. And the other one is blackbody, especially for the neutron stars and basically any bunch of collection of matter that has vast amounts of helium and hydrogen and are producing X-rays. We are getting this new trend of power law shape in the basic statistics. And in astrophysics, especially in the spectral analysis, people are generally using chi-squared analysis. Basically, they are fitting a model to an observation, and then they are looking at how much deviation do they receive from one fitted model. It is a way to test how much accurately your model is describing that observation, basically. So this was what we did as a part of chi-squared analysis. We used a collection of software developed by NASA called HeSoft. So by using HeSoft, we made some X-ray analysis, especially to investigate the further in the spectra of the sources. But all of those things, actually, I think passed with as if like a let's play video game YouTube session. So basically, I did some analysis that I was doing when I was an undergraduate in my first parts of going into this field, and I wanted to the main idea of me showing you these observations and analysis was to navigate you, was to show you the places that you can do this. But I think in the first parts of this course, I said like, don't think that after taking these after watching these 6 videos, you became an astronomer and then became a scientist. It doesn't work like that. People spending their lives in this field. But I think at the end of this course, what you are achieving is that you are able to obtain and make critical thinking about this part of this physics. So basically, after this course, whenever you read a textbook, whenever you read a scientific article or a popular science article, you will say, "Oh, I heard about that. This means that. So if this is that, so you will be more able to connect the dots between different phenomena." This was the initial aim of this course. So I think how much we achieve that is depending on how much you spend time and then looked around, do more investigation about these fields. So I hope this course provided you an encouragement and also an enthusiasm to go deep into your researches, widen your researches, and then I hope also this course enlarge your view about certain parts of the universe that are highly energetic. So thank you very much for actually joining this course and watching this overall summary as well. And right now, I believe if we have questions, I am ready to answer them. More than happy. Okay, sure. No problem. Yeah, yeah. Okay, so yeah, sure. Well, so you're not audible means that they're not able to see you, right? Or hear you. Okay, okay, perfect. So yeah, basically let me summarize about this course one more time and then also wait for questions. So like this is your final chance. If you have questions, you can on live ask me. But if you take this course in the future and then also have questions, I am completely accessible. I can share my contact information after this live stream basically. So this course is basically consistent of 6 lectures. They vary from 45-50 minutes to 1 hour, but it is like most of the time it is very piled up with information. So be ready for that. I think if I was taking this lecture and if I was an undergraduate, I would probably not be able to just watch the 1 hour video and then just continue my life. I would probably pause at some points and then take some notes. This was my perception of the course. So basically, with the help of this course, you will be able to get the brief idea of different spectra of light and how we are conducting academic analysis, like astronomical analysis in infrared, optical wavelength, radio, ultraviolet, gamma rays, and X-rays. But this course is primarily focused on X-rays and gamma rays. In addition to those electromagnetic light, we are also able to, we will be also looking about how people investigate objects and do analysis in cosmic rays and also gravitational waves as well. This was the first idea of this course. The second part also, you will learn about physics and astronomy behind some of the very famous astronomical sources, such as black holes, neutron stars, supernovae, supernova remnants, or X-ray binaries, giant stars, energetic stars, and basically everything that is producing high energy particles in the universe. We are giving you all the different information about all those different sources. You will be also able to learn basic engineering details, technical details of astronomical instruments, primarily X-rays and gamma rays instruments, how we are catching those photons, how we are collecting that information. You will also learn the history of this field. And then finally, you will go into the high energy astronomy software of NASA, HeSoft, and you will learn how to download and calibrate an observation in X-ray astronomy, and then do some spectral analysis. This was the whole aim of the course. Yes. Sure. Okay. So yeah, also I should also mention you that we have a Discord channel for this. We have a Discord server for this course. So basically, whenever you have this course, whenever you enroll to this course, you will also add it to our Discord server, which I am usually online. I love Discord. It's a nice environment. It's a nice. It is not a replacement to our physical world, but it is a nice environment basically if you know how to use it nicely. So you will be able to contact me and then ask me any questions you have about every part of the course. I will be totally accessible for that. At the same time, I believe also I will also show you some textbooks that this course is based on, so that you will be able to get more information as well. Yes, I'm talking these things in order to get you to give you a final opportunity to ask you some questions. But if I presume, well, I guess everybody understood properly, so that we have this information. But also, to be fair, I get a lot of questions throughout the lectures, so the people were really interested in these courses. All right then. So if you are interested in this course, I encourage you to enroll and take a look. At the same time, you can always feel free to contact me if you have any questions, anything. As I said, we will also have a Discord server so that you will be able to ask you some questions from there as well. Apart from that, feel free to follow AstronEra. Oh, one final remark. I am currently. In fact, I guess I should have needed to introduce myself for in case there are some audience who is not. But basically, yeah, in case you don't know, I am Özgür. You can call me Oz. I am studying physics. I'm basically doing my master's degree in in high energy astronomy in astrophysics in Middle East Technical University. I am also a project assistant there. And I am also, for about 6-7 years, I work as a dinosaur in Meteo Amateur Astronomy Club. So actually, AstronEra was also in collaboration with Meteo Amateur Astronomy Club for this particular course. So I want to also say hi to my friends from Turkey who were also taking this course as well. Yeah, I believe if you don't have any questions, it was a pleasure speaking to you one more time, and I would like to thank AstronEra and Shweta, my dearest friend, for having me this opportunity to provide you this beautiful course, and hope to see you some other time. I would love to continue this collaboration and do some mutual stuff with people who are interested in astronomy in India and also in Turkey as well. Let's aim for that. All right. Okay. See you everyone. Goodbye.